My name is Yamato Abiru. I'm a student at National Institute of Technology Sasebo College in Japan. And now I'm talking about non-destructive detection of internal pipe crust in hydrogen energy systems. Today, I'll talk about introduction and specimen preparation and non-destructive testing and the conclusions. First, introduction. Recent years, toward carbon neutrality, clean energy is being developed in the world. Against this background, zero carbon dioxide emissions, high energy efficiency, and can be produced from a variety of resources. For these reasons, increasing number of facilities are using hydrogen. This picture is fuel cell Mirai and fuel cell train Hibari. Those are developed in Japan. Hydrogen society will be reality. But important issue in using hydrogen. This is called hydrogen embrittlement. This is the decrease in material strength caused by hydrogen atom entering the metal. Figure 1 shows a photograph of fatigue crack in hydrogen gas and the air. As shown, this figure, characteristic of hydrogen embrittlement cracks are either rapid crack propagation. For this reason, accelerated fracture of structures. So high resistance to hydrogen embrittlement material is used in facilities of using hydrogen, for example, aluminum alloy and stainless steel, but these materials at a high cost, so hindering the realization of a hydrogen society. Therefore, we are focusing on hydrogen station and replacing structural material with low carbon. But there is a problem with that. The problem is crack propagates faster due to hydrogen embrittlement. To be resolved, development of hydrogen embrittlement prevention coating and high precision non-destructive testing technology. By developing these, safety and economy can be combined. The objective of this study is to establish non-destructive testing technique for hydrogen embrittlement cracks. Okay, specimen preparation. We conduct quasi-cyclic internal pressure tests to prepare specimen with different crack lengths. Figure 2 shows the illustration of this test. In this test, figure crack propagate from inner to outer surface. About experimental conditions are shown here. Material is used to STKM. Figure 3 shows a photograph and the dimension of specimens. The thickness of the specimen is 4 millimeters. About hydrogen contents, from now on, 0 mass ppm will be denoted by the uncharged specimen, and 10 to 11 mass ppm will be denoted hydrogen pre-charged specimen. This is the result of quasi-cyclic internal pressure test. Figure 4 shows displacement cycle number curve and a fracture surface photograph. The vertical axis shows testing machine head displacement, and the horizontal axis shows number of cycles. As shown in figure 4, hydrogen pre-charged specimen are ruptured at about 20,000 cycles, while uncharged specimen are ruptured at 450,000 cycles. After this test, cracks and dents were observed in the specimen. This is more detailed crack length illustration. Fatigue crack propagates through the pipe with each applied load, like this illustration. Table 1 shows specimen made by this test. And then attempt to prove using multi-type non-destructive testing. Okay, non-destructive testing about eddy current testing. I will briefly explain about eddy current testing. Alternating current is applied to the extension coil, and then eddy current generates in pipe detected by detection coil. And then providing by the difference in response of detection coils. About the experimental condition shown here, in the reference is used pure specimen and with dense specimen, and specimen and hydrogen precharged specimen, crack length 4 mm. In this study is used until specimen crack length 2 mm and hydrogen precharged specimen 2 mm. Other information is referred to reference 1. Okay, this is the result of eddy current testing. The figure 7 shows pure specimen test result. The vertical axis shows voltage value, and the horizontal axis shows distance from its end of steel pipe specimen. As shown figure 7, no change in voltage value was observed. Okay, next, figure 8 shows with dense specimen. As shown, this figure, dense peak around 110 mm through 103 mm. Figure 9 and figure 8 shows untouched and hydrogen precharged specimen with crack length 4 mm. Both of the result, dense peak around 110 through 103 mm. In addition, voltage change due to crack after dense peak. Okay, figure 11 and figure 12 shows untouched and hydrogen precharged specimen with crack length 2 mm. Both of result, dense peak was seen as in figure 8 through 10, but no change in voltage value was observed after dense peak. For this reason, we found that the crack was not being improved. The crack length 2 mm. Okay. Next, hammering testing. Hammering testing is formed vertical waves by hammering stick. Then peak are generated by resonance between vertical waves and the natural frequency of the material. And then inspect by change in natural frequency due to defects. Experiment condition is shown here. Hammering position is crack point at center of specimen. Okay, this is the result of hammering testing. Please look at this figure. The vertical axis shows normalized amplitude spectral intensity. The horizontal axis shows frequency. This figure shows same result. And this one is the result of with only dense specimen. Below the red line and the left figure is uncharged specimen with crack lengths 1, 2, 3, and 4 mm. But right one is hydrogen precharged with crack lengths 1, 2, 3, 4 mm. Okay. Let's compare over 50 analyzed results. The 8 through 9 kHz peak for almost all results. This indicates that the change is in peak is due to structure of the drill. Next, if length and crack length 1 mm or greater result is reduced 5 kHz peak compared by pure specimen. This indicates that the change in peak is due to them. Until specimen crack length 1 mm or greater and hydrogen precharge with crack length 2 mm or greater result is increased 3 to 4 kHz peak. This indicates the change in peaks is due to crack. So hydrogen crack, we successful to detect. But with dense specimen and the crack length, with dense specimen and the hydrogen pre-charged specimen crack length with crack length 1 millimeter, equivalent 3 to 4 kilohertz peak. So in the hydrogen pre-charged with crack length 1 millimeter have not been explored. In summary, success crack provided in case uncharged specimen 100 millimeter or greater, and hydrogen pre-charged specimen crack length 2 millimeter or greater. Okay, next ultrasonic testing. This is when applied ultrasonic wave to the material. Ultrasonic wave direct from crack, defect, and so on are measured. Detect defect using the magnitude and the propagation velocity of the reflect wave. Condition is shown here. Detection method is used angle beam inspection method, and the ultrasonic beam is emitted at 70 degrees. Probe position is 5, 10, 20 millimeter from center of specimen. This is the result of ultrasonic testing. Figure 16 shows pure specimen test result. And A is 5 millimeter, B is 10 millimeter, and C is 20 millimeter. The vertical axis echo height, and the horizontal axis shows distance from group. As shown, A and B, echo height was approximately 20%. But as shown, C, about 35 of the value was found 0 to 1 millimeter distance from group. So surface occurring may be related. About uncharged specimen with crack length 3 millimeter test result. As shown, A and C echo height equivalent to pure specimen, like 20%. But as shown, B shows 35% of echo height, occurred around 4.35 millimeter from our group. So this indicates a posterior effect of crack. Next, hydrogen pre-charged specimen. As shown, A and C as same to pure specimen, but as shown, B also shows 41% of echo height occur around 8.1 millimeter from the group. It's also possible effect of cracks. Okay, final conclusions. About the eddy current testing, uncharged and the hydrogen pre-charged specimen with crack length 2 millimeter could not be proved in voltage value. Hammering testing, uncharged specimen with crack length 1 millimeter or greater, and hydrogen pre-charged specimen with crack length 2 millimeter or greater, a peak change due to crack and dent could be broad. Ultrasonic testing, uncharged hydrogen pre-charged specimen crack length 3 millimeter, echo height not found in pure specimen was detected. Okay, future outward continue to improve the ocularity of existing methods like eddy current testing, hammering testing, ultrasonic testing, and further validate with new methods like acoustic emission testing, like that. Okay, thank you for your attention.
Thanks for your great talk. So we have time for a few questions.
Thank you. That's a very interesting topic now with the whole transition to clean energy. It's probably caught my attention. You got to the last one.
Last one.
Yeah. did you check, did you apply voltage? That also has to do with my ignorance of the topic. The technique. Did you apply voltage to a pipe filled with hydrogen?
Yes, hydrogen. Hydrogen.
Full of hydrogen. Okay.
But in content hydrogen from pipe and testing.
Okay. So again, this is not my ignorance of the subject. Isn't it a risk hazard to apply to you know to produce a spark and an explosion because of the hydrogen?
Is that the hydrogen is a dangerous gas, but I like to coating the pipe, so not
Okay.
so not
It's coated inside, so
Yeah, inside.
the conductivity.
it's a pipe
Okay.
coating.
Okay. Thank you.
Thank you for your question.
Another question? Then a final question from my side. Can you say something about the depth of the material which is affected by recharging with hydrogen?
The depth of then
Yeah, I mean, how deep is it diffused inside the material?
It can inside this testing.
金属の中にどれだけ水素が入ってるかっていう、どれだけ拡散してますかっていう。
Then okay, hydrogen content in 3 days in the solution. So we research about the hydrogen content in relationship of the day and day in the solution. So 3 days is completed the hydrogen content. So we decision 72 hours. It's fully
Okay.
hydrogen.
Yeah.
Thank you.